Okay, thank you for the introduction, and thanks to the organizers for organizing this conference and letting me speak. So this talk is again about the null distance just as Brian's, and I used the 10 minutes in the meantime to write some stuff that is kind of basic, so I wanted to go through it quickly. The first global hyperbolicity that is in the title, it's just defined as causality, so there are no closed causal curves in my spacetime, and the causal diamonds are compact, so these points that are kind of causally sandwiched between P and Q. And just some remarks about that. So historically, there were stronger conditions here, but Bernard and Sanchez showed that causality is enough. And then Hohnkop and Minguzi showed that even causality is not necessary if M is non-compact and has dimension larger than 2. And then one thing I kind of vague that I want to say, because also it will motivate one of the theorems in the talk, is that global hyperbolicity in the Lorentzian setting is in a way analogous to completeness in the Riemannian setting. So why do I say that? So, well, in a way, this is a bit similar to the condition of closed balls in a Riemannian manifold being compact if the manifold is complete. But also maybe more importantly, if you're globally hyperbolic, then you have a maximizing geodesic. Oh yeah, sure. If you are globally hyperbolic, then you have a maximizing causal geodesic between any causally related points. And if you're a complete Riemannian manifold, then you have a minimizing geodesic between any 2 points. And also a theorem that I will give later will kind of emphasize this aspect. Okay. And now another theorem that motivates this talk is the fact that global hyperbolicity is equivalent to the existence of a Cauchy time function, or temporal, as was shown later. So I'm going to define what these are just to make the talk more self-contained. Yeah. Sorry, but a Cauchy time function. I'm going to say now. Basically, it's one where each level set is a Cauchy surface. So basically, if I have a real valued function on the spacetime manifold, I say it's a time function if it's continuous and it's strictly increasing along every future directed causal curve. Or gamma future directed causal. I'm going to say it's temporal if it's, let's say C infinity could be lower, but it has to have a differential, because I'm going to ask like the infinitesimal equivalent of this condition, which is to say that the differential of tau acting on a causal vector, a future directed causal vector, should be strictly positive. Okay. And now the Cauchy part. So if additionally as I said, every level set is a Cauchy surface, which you can rephrase by saying that the image of tau along an inextendable causal curve should be the whole real line. Okay. This is the background in terms of just Lorentzian geometry. Now, for the talk to be self-contained, I will define the null distance again, but it's exactly the same as in Brian's talk. Here. Okay, and again, the idea is to do Sormani and Vega. And okay, maybe just to say first what the philosophy is. So we want to go from, if you want the category of Lorentzian manifolds with a time function, I have a Lorentzian manifold equipped with my time function. Then I want to go to, you want the category of metric spaces. And if you want, you can retain the information about the function, so with the continuous function, let's say. And just to introduce the notation, so the distance I denote by d hat tau. And it just defined as follows. So I take my 2 points, and then I take the infimum of the null length, which I will say now what it is, over piecewise causal curves from P to Q. So I have my piecewise causal curve, and then I label the breaking points where it goes from future directed to past directed. I label them by beta 1, beta 2, beta 3, beta 0 is starting point. And then the length was just the sum of the increments of the time function along each piece. Okay. All right, and then, well, some remarks that, again, Brian already did, but they're important for this talk also. So first, it's conformal invariant. By which I mean that if I replace my spacetime by another spacetime where I just take the same metric multiplied by a function, and let's say, and I take the same time function, then nothing changes. And the other thing is that it's a pseudometric in general, but it's actually a real distance if tau is locally anti-Lipschitz. And I'm always going to assume this. I don't really want to deal with non-anti-Lipschitz time functions. Okay. Right. So what's the goal of this talk now? So the goal is that we want to encode causal information about the space-time in the null distance. And notice that because it's conformal invariant, the causal information is really the only information that you can put in it, except maybe if you think of the time function as being a special one, such as the cosmological one, and in some sense thinking about this information that it's a special one being retained also here. But that's not really the point of view I'm going to take. I'm going to take the point of view that we have like all sorts of time functions, and therefore I will only look at causal properties of the spacetime. And then, So the observation that was made already by Sormani and Vega was that on the one hand, if your points are causally related, then the null distance is exactly the difference in time function, because the causal curve that connects them is in particular a piecewise causal one, and it is going to be distance realizing, because going up and down will only make you longer, it will never make you shorter. So this we always have. And then they raise the question, when is the opposite one true? Okay. And again, as Brian said, the answer cannot be always, because clearly if you remove a point, for example, you create an obstruction for having a causal curve, but you could still have a sequence that goes around it and that makes the null distance being exactly this. Okay. And then, now the answer. So first, I will state the theorem due to Anna and Christina Sormani. That was also in Brian's talk. So, which says, well, so two things. So in a way, locally always. So for any, well, any locally anti-Lipschitz, which I said I'm always assuming, for any locally anti-Lipschitz time function, locally you have here if and only if. And globally, if tau proper, so pre-images of compacts are compact. But this is not, as I will now explain, this is not a necessary condition. It's sufficient, but it's not necessary. And in fact, together with Annegret Burtscher, we have a similar result. Which is the following. So globally, for tau a Cauchy temporal function. So notice that we have made a stronger assumption in assuming that our function is temporal instead of just a time function. But on the other hand, we don't need the properness assumption. And we have replaced that by the assumption that it's Cauchy. Yeah. This one, yeah, exactly. So, right. If there is time, I will say something about the proof, but first I wanted to say something about another result. So what we have done for now is we have said, well, when you take a spacetime and you transform it into this metric space with a time function, and now you have 2 points in here, and you're wondering, are they causally related or not? How can you find out? Well, using this equivalent. But a sort of related question is there a correspondence between causal properties of the spacetime and metric properties of the null distance. Yep. And well, the answer is yes. Because in a way we can encode global hyperbolicity via completeness of the null distance in the following sense. So you have that the spacetime is globally hyperbolic if and only if there exists a time function such that the null distance is complete. Okay. So now I want to prove this one first because it's short. Okay. Yeah, I agree, yes. It is more general in the spacetimes that we allow, but it is less general in the time functions that we put on them because ours are differentiable and these could be just continuous. So neither of these theorems implies the other. Yes, I agree with that. So I claim what Miguel says, and I agree, is that if you have a proper time function, then the spacetime must be globally hyperbolic with compact Cauchy surfaces. But what I'm saying is that this tau could be not differentiable. And we are assuming it's temporal, so it has to be, it was there, differentiable with the time-lag gradient. Right. Okay, so I will prove this 3 now. So first, this direction. So how do we do that? So what we want to show is that if the null distance is complete, then the time function tau is Cauchy. And then by the theorem 0, we are done, because having a Cauchy time function is the same as being globally hyperbolic. And how do we show that? So, well, we pick an inextendable causal curve. Okay, I assume it's parameterized on R, but this doesn't mean anything special. Okay, and now suppose that the supremum of the time function along this inextendable causal curve gamma is some finite constant. So notice that by definition of a time function, this is increasing, and therefore the supremum exists. The question is only, is it finite or infinite? And if it's infinite for every such gamma, then we satisfy the definition of being a Cauchy time function. So let's assume there is one gamma where it's finite. What happens then? what happens then is that, again, as I said before, and I think Brian said, a causal curve is null distance realizing. So the null distance between 2 points on the curve is just given by the difference in their time functions. Okay, and now this has to go to 0 when, for s and t go to infinity. So because the supremum is finite, it means that kind of both of these have to tend to c, so this will go to 0. But that would imply that now this sequence of points given by evaluating gamma on natural numbers is a Cauchy sequence for the null distance. And then by assumption that the null distance is complete, there exists a limit. And this is a contradiction to the fact that gamma is inextendable. Okay. So this proves one direction. So we've proven now that if the null distance is complete, then tau is a Cauchy time function, and therefore the spacetime is slowly hyperbolic. Now we want to show the other direction. Let's see there maybe. So how are we gonna? So the other direction is in a way the hard one, but most of the hard work was done in other papers, and we just kind of have to put the pieces together. So we continue proof of 3, and now we want that one. We will use a theorem for this. Maybe if I number them, this should be now 4. And this was shown independently by Bernard and Zua and by Minguzzi. And it says the following, so it's yet another characterization of global hyperbolicity. So it says via time function, so it says a spacetime is globally hyperbolic if and only if there exists something called an H-steep temporal function. Which again I will denote by tau. So what is that? So a function is called H-steep temporal if the following holds. So if the differential applied on any causal vector is larger or equal than the Riemannian norm of the same vector with respect to some complete Riemannian metric H. So this H here is represents a Riemannian metric, and it should be a complete one. Okay, and this should hold for all the future directed causal. And I mean, you can see that this is a stronger condition than temporal, because temporal was just saying this should be larger than 0, and now we're putting a lower bound by some norm of some Riemannian metric. And then I'll erase this. Up until 25, right? Okay, and now what happens when we have such a H-steep temporal function and we take the null distance? So what happens is, suppose beta is a piecewise causal curve and we want to compute the null length, then one way to rewrite the null length instead of the sum that I just erased is to write the integral of the absolute value of the gradient applied to the tangent vector. Okay. And now, by definition of H steep, I can bound this from below. And what I conclude is that the null distance between 2 points is actually bounded from below by the Riemannian distance measured with respect to H. Because I see that the piecewise causal curves have a longer null length than they have an H length, and moreover, to compute dH, you minimize over a larger class of curves, so it's going to make it maybe even smaller. So we have this for all points. And then we are done. Because now if we have a Cauchy sequence with respect to d tau hat, then it's Cauchy with respect to dH, and therefore there exists a limit because H was complete. And being a limit, it doesn't depend. It's a topological property, so we're done. Yes, correct. Right, I should have said that. So the d tau hat induces the manifold topology. And also, maybe let me say that kind of part of this last part of the argument was also in the paper by Brian and Annegret, but not in connection with the H-steep temporal function. Well, the thing is, if you take a causal diamond, well, you would have to think what an H-steep temporal function on the diamond is. I'm not sure, but I think the level sets would look somehow like this. So obviously, Well, not necessarily proper. I don't know. Well, maybe. No, because these points are not included, right? I don't think it would be proper. In some, I think in some way the oh, okay. I mean, maybe I can say it anyway. So I think the idea would be just that the kind of the level sets would accumulate at the boundary, and in a way, if you approach the boundary, you have to, your tau has to grow like very fast, and that makes the null distance be very long. Thanks for your question. Okay, so there's 10 minutes. Okay. Let me erase something. Okay, let me say comment a little bit on the proof of theorem 2, although it's much longer, so I cannot give the whole thing. So the idea is the following. So consider 2 points, because let's see. Right, we want to show that we have the if and only if in this star expression there. So consider 2 points in M, and then let beta n, so such that their null distance is the difference of time function. Okay, and then let beta n be a sequence of null distance minimizing piecewise causal curves. Or let's say like this. Be a null distance minimizing sequence is a better way to say it. Okay. So then, what do we want to show? We want to show that in some sense, the sequence of curves beta n converges to some limit curve beta, and that beta is a causal curve from P to Q. Okay, so maybe a bit the idea, we have PQ, we connect them by some piecewise causal curves, and now if in the limit the length has to tend to this, it means that each time we have to go less and less down and just go as much up all the time as possible. And then the intuitive idea is that in the limit, we just go up the whole time. Right, and in fact, in the theorem 1 of Anna Sakovic and Christina Sormani, the philosophy is the same, but the sense in which you take the limit is different, and the way how you prove that it's causal and that it reaches from P to Q is different. Okay, but in a way, I mean, this basic idea is like the logical thing to do in this case. And now I can say a little bit just how I take the limit. So the idea is, because tau is temporal, we can write G, the Lorentzian metric, as just something proportional to d tau squared plus something orthogonal. And note that we have assumed that the coefficient here is exactly -1. Because otherwise we could take a conformal transformation to remove it. Okay. And now what we will do is something that the physicists call Wick rotation. So we just say, okay, let's here where we have a minus, we're going to put a plus. And this defines the Riemannian metric. So now we want to use what we would like to do naively is to parameterize the beta n's by the arc length of this Riemannian metric and apply the Ascoli-Arzelà theorem. But to do that, we would want this to be a complete Riemannian metric. And for some time, I thought that global hyperbolicity of this would imply completeness of the Wick rotation. But it turns out it's false, and there's an explicit counterexample by Miguel Sanchez. So what we will have to do is put a conformal factor on it to make it complete. And then the idea is that, yeah. Well, what is written on this side of the blackboard doesn't depend on P and Q, so this you just. No, because, well, in a way, ultimately, yes, because it's globally hyperbolic, but kind of it's what you want to prove. Because, look, if you had, yes, but I mean, so, okay, so here's the thing. A priori, I don't have a control on the Riemannian length of beta n. It could be that they become infinitely long, and that then when you take the limit kind of goes to infinity before reaching Q. I can give maybe an example. I don't know if it exactly answers your question, but suppose that we're, say, in the Sitter space, and we have a non-compact causal diamond like this. Now, I can find you a sequence of causal curves that, because they're causal, they realize the null distance, and that kind of goes to infinity. And now the limit of this sequence is going to be just this one, and it goes to infinity, and it never reaches Q. This could happen in principle, and we have to show it doesn't. Right, but how that really plays into the proof is not so obvious. Yeah? So maybe also I like to give this picture because it shows that you really do need to be in a globally hyperbolic space-time to expect a global encodation of the causal relation. Because otherwise, exactly this can happen. And in fact, in the paper, we have an example which is like this, but with an extra dimension. And there we see that even though it's causally simple, so one step lower on the causal ladder, the causal relation is not encoded in the null. And I have 1 minute left, so maybe just as a bonus yeah. Sorry.
2 minutes because
Oh, thank you. Maybe just as a bonus, so a bit the idea here is that the length of this Riemannian metric relates nicely to the null length, and in fact, we can show that the null distance is locally by Lipschitz equivalent to the distance given by this Riemannian metric. And then, because all Riemannian metrics are locally by Lipschitz to each other, we conclude that if you do the null distance for 2 different time functions, what you get is locally by Lipschitz equivalent. So this maybe answers a bit Andreas' question. But globally, it can be very different. So that was his thing.